You can spend your whole life moving and still not escape the sun's family. Right now, something we built is leaving the solar system. It has been flying since 1977. It has crossed and that's at the speed of one of the fastest human-made objects ever launched away from the Sunday. Now let's talk about the fastest thing we've built that doesn't just drift outward. The Parker Solar Probe. It dives toward the Sunday. It steals orbital energy from Venus through gravity assists. It swings past the sun at blistering speed. At its peak, it moves over 400,000 miles per hour. That sounds insane. It is insane. It is a masterpiece of trajectory design. But if you aimed it at Proxima Centauri and somehow kept that speed constant, it would take thousands of years to arrive. Thousands. That's longer than recorded human history. So when people say, we just need better rockets, this is what they're up against. It's not about doubling speed or tripling it. The distances don't care about small improvements. The gap between us and the stars is not a crack, it's a canyon. And here's the twist most people miss. The problem is not that we are slow. The problem is that space barely changes when you move through it. Imagine driving across the desert. Hours pass. The view shifts slightly. Distant mountains inch sideways. The road hums under you. There's motion everywhere. Now remove the road, remove the air, remove the landmarks. You are in a black ocean with a few bright points, fixed so far away that your movement does not change their position in any noticeable way. For most of the trip, the view will never seem to change. That comment is not pessimism, it's physics. Stars are so far apart that even traveling at tens of thousands of miles per hour barely shifts your perspective over decades. Constellations would look frozen. The sky would feel static, motion without progress. This is where your intuition breaks. Because on Earth, speed equals change. Speed equals arrival. In space, speed often equals drift. And here's the uncomfortable truth. If you want to reach another star within a single lifetime, you cannot think in terms of current speeds, not Voyager speeds, not Parker speeds, not anything powered by chemical fuel. You have to start thinking in fractions of the speed of light. And that's when the real antagonist steps into view. The speed of light is not just fast, it is a limit, a hard one. It is written into the structure of space-time itself. You cannot cross it, you cannot match it if you have mass. The closer you get, the more the universe pushes back. We haven't even reached 0.1% of light speed with anything carrying meaningful mass. And meaningful time dilation, the thing that lets a traveler age slower than the people left behind, doesn't really kick in until you pass 10% of light speed. 10%. That's about 100 times faster than Voyager. This is where the map starts to fight you. You think the problem is fuel. It isn't just fuel. You think the problem is engineering. It isn't just engineering. The deeper problem is that distance and time are tied together in a way your brain doesn't naturally understand. You don't just need to move fast, you need to bend how time flows for you. And that sounds like science fiction. It isn't. But it comes at a price most people don't think about. Because if you go fast enough to make the stars reachable in your lifetime, you are no longer just traveling through space. You are traveling forward through history. And you may never return to the era you left. That was only the beginning of the problem. We haven't even opened the fuel tank yet. The fastest we can go still isn't leaving. Let's climb the ladder. Chemical rockets are what carried us to the moon. They burn fuel. Hot gas blasts out the back. Newton's third law pushes you forward. Simple, violent, reliable. But chemical energy comes from breaking molecular bonds, and those bonds release a fixed amount of energy. You cannot negotiate with chemistry. You cannot convince hydrogen and oxygen to give you more than they physically contain. This is where the Tsiolkovsky rocket equation enters the story. It's not a machine, it's not a material, it's a formula, and it is ruthless. In one sentence, it says this: the faster you want to go, the more fuel you need, but not linearly, exponentially. That word matters. If you want to double your speed, you don't double your fuel, you multiply it far beyond reason. Each extra gain in velocity demands more propellant than the last. Soon, the rocket becomes mostly fuel carrying fuel carrying fuel. You thought more fuel means more speed. Evidence shows more speed means absurd fuel mass. That implies chemical rockets can never scale to interstellar travel in a human lifetime. You hit a wall, and it's made of math. Gravity assists help. We've used them for decades. You swing by a planet like Jupiter and steal a bit of its orbital momentum. Voyager did it. New Horizons did it. Parker Solar Probe dives past Venus again and again to reshape its path. A gravity assist is like borrowing a tiny fraction of a planet's motion. The planet slows down by an amount too small to measure. The spacecraft speeds up by thousands of miles per hour. It feels clever. It is clever. But there are only so many massive planets in useful positions, and each assist costs time. Years between flybys, decades of choreography. You can't slingshot your way to light speed. The solar system simply doesn't have enough to give. So we try ion propulsion. Ion engines don't burn fuel in explosions. They ionize gas, usually xenon, and accelerate charged particles with electric fields. The exhaust velocity is far higher than chemical rockets, much more efficient. The Dawn spacecraft used ion propulsion to orbit both Vesta and Ceres. That was historic. It could thrust gently for months, slowly reshaping its orbit with extreme precision. But here's the catch. Ion engines produce tiny thrust, about the weight of a sheet of paper pressing on your hand. That's it. It works because there is no air resistance in space. Given enough time, even a gentle push builds speed. But enough time means years, decades. You can't strap humans to that and expect to cross light years before they die of old age. So we look at nuclear thermal rockets. Instead of chemical combustion, you heat hydrogen with a nuclear reactor and expel it. The NERVA program in the 1960s proved this works. Nuclear thermal propulsion roughly doubles the exhaust velocity of chemical rockets. Double sounds powerful. It isn't enough. Doubling exhaust velocity improves the rocket equation, but not by the orders of magnitude needed. You might shave thousands of years off a trip to Proxima Centauri. You still have thousands left. Then there are solar sails. Photons carry momentum. Light can push. The Japanese spacecraft Icaros demonstrated this in 2010 with a thin reflective sail. No fuel, just sunlight pushing against a mirror. Elegant. Beautiful. Near the sun, radiation pressure is strongest. You could, in theory, dive close, unfurl a massive sail, and let sunlight accelerate you outward. But radiation intensity drops with the square of distance. Double your distance from the sun, and you get a quarter of the push. Soon the sail coasts. And interstellar space offers almost no radiation to keep pushing. Even if you reached several 100,000 miles per hour, the nearest star would still require thousands of years. This is where people say, what about nuclear bombs? Project Orion studied exactly that. Instead of one big engine, you detonate small nuclear charges behind a massive pusher plate. Each explosion kicks the spacecraft forward. It sounds insane. It was studied seriously. Freeman Dyson worked on it. Orion could, on paper, reach a few % of light speed. That's huge compared to anything we've built. But a few % of light speed still means a trip to the nearest stars takes over a century. And time dilation at those speeds is tiny. The crew ages almost the same as everyone on Earth. So even our wildest practical ideas barely dent the problem. You see the pattern. Chemical fails, ion fails, nuclear thermal fails, solar sails fail, nuclear pulse helps, but not enough. The universe doesn't block you, it invoices you. Every gain in speed comes with a bill. And now the antagonist steps fully into frame. The speed of light. In vacuum, light always travels at the same speed, about 186,000 miles per second. It doesn't matter how fast you're moving, you will still measure light moving at that speed. That sounds harmless. It isn't, because if light's speed is constant for all observers, Something else must adjust to make that true. Time adjusts. This is special relativity. If you move fast enough, your clock slows down relative to someone at rest. This effect is called time dilation. It is not science fiction. It has been measured with atomic clocks on airplanes and satellites. At everyday speeds, the effect is tiny. At highway speed, the difference is meaningless. Even at orbital speeds, it's small. But as you approach a significant fraction of light speed, the effect grows. Physicists describe it using the Lorentz factor, often called gamma. Gamma tells you how much time stretches and how much length contracts. At half the speed of light, gamma is about 1.15. That means time on the spacecraft passes about 15% slower than on Earth. Not dramatic. At 90% of light speed, gamma is about 2.3. Now things shift. 1 year on the ship equals more than 2 years on Earth. At 99% of light speed, gamma is about 7. That's when the story bends. You thought the only way to cross 4 light years was to spend 4 years. Evidence shows that for the traveler, the trip can feel shorter. That implies distance is not absolute. It depends on your motion. Here's the key. From Earth's perspective, nothing beats light. If a star is 4 light years away, light takes 4 years to arrive. But from the traveler's perspective at high speed, the distance in front of them contracts. This is length contraction. Space itself shrinks along the direction of motion, so you are not just moving through space. Space is changing shape for you. Imagine 2 identical twins. One stays on Earth, the other boards a ship traveling at 99% of light speed to a star 20 light years away and comes back. On Earth, the round trip takes about 40 years. On the ship, because of time dilation, the traveler experiences far less, maybe 6 or 7 years each way. When they reunite, one twin is decades older than the other. This is the twin paradox. It is not a paradox anymore. It has been confirmed experimentally. The asymmetry comes from acceleration. The traveling twin changes frames. The Earth twin does not. This is the loophole. The speed limit does not just slow you down. It reshapes time. And for the first time in this story, there is a path to the stars within a human lifetime. But this is where the cost becomes personal. If you travel fast enough to make the trip short for you, it is long for everyone else. You can cross tens, hundreds, even thousands of light years in what feels like decades aboard the ship. But when you arrive, Earth has aged centuries, millennia. You have outrun your era. This is no longer a fuel problem. This is a choice. Fuel doesn't scale. It explodes. Now that you've seen the loophole, you might think the only remaining challenge is engineering. Build a powerful enough engine. Push to 99% of light speed. Let time dilation do the rest. But the universe doesn't hand out relativistic speed cheaply. The faster you go, the more energy you must pour into motion. At low speeds, the relationship is simple. Double your velocity, and your kinetic energy quadruples. That's basic Newtonian physics. But as you approach a significant fraction of light speed, Newton's rules stop telling the full story. Relativistic energy takes over. The same gamma factor that stretches time also multiplies energy. As velocity climbs, gamma climbs. And as gamma climbs, the energy required to accelerate climbs with it. At 90% of light speed, your kinetic energy is already more than double what classical physics would predict. At 99%, it's far worse. You thought the rocket equation was cruel. Relativity is colder. Here's the brutal symmetry. If you want to reach a distant star and actually stop there, you must pay twice. Once to accelerate. Once to decelerate. Speed is not enough. Arrival requires braking. That doubles the bill. Consider accelerating a modest spacecraft to 90% of light speed. The energy required rivals the output of entire civilizations over vast spans of time, and that's for something small, not a floating city, not a generation ship, something barely capable of supporting human life. You thought more fuel meant more range. Evidence shows more speed demands energy on stellar scales. That implies propulsion must tap into physics beyond chemistry, beyond simple reactors. So we look to fusion. Fusion powers the Sunday. It fuses hydrogen into helium and releases enormous energy in the process. If we could harness controlled fusion for propulsion, exhaust velocities would dwarf chemical rockets. Project Daedalus studied this in the 1970s. A fusion-powered probe, massive, thousands of tons. It would burn fusion fuel for years, pushing itself to roughly 12% of light speed. 12% sounds transformative. It isn't. At 12%, time dilation barely helps. Gamma is about 1.007. That means for every 100 years on Earth, the traveler experiences 99. Fusion can shorten journeys to nearby stars to decades or centuries, but it does not bend time enough to keep everything within a single normal lifespan. To make relativity work in your favor, you need to climb higher. 50%, 70%, 90%, and that is where energy becomes monstrous. Enter antimatter. When matter meets antimatter, they annihilate completely, converting mass directly into energy through E equals mc squared. 1 gram of antimatter reacting with 1 gram of matter releases as much energy as a nuclear bomb. It is the most energy-dense fuel we know. On paper, antimatter propulsion could push spacecraft to a large fraction of light speed. It transforms the rocket equation from impossible to barely conceivable. But antimatter does not exist in useful quantities naturally. We have to manufacture it in particle accelerators, and the production rate is microscopic, nanograms per year globally. To fuel a relativistic spacecraft, you would need kilograms, thousands of times more than humanity has ever produced. And storing antimatter is its own nightmare. It annihilates on contact with normal matter. You must suspend it in magnetic traps, keep it perfectly isolated. For decades, this is where the universe adds another clause to the invoice. Even if the physics allows the speed, your civilization must command energy flows comparable to stars. And even then, the story doesn't get easier, because as you approach high relativistic velocity, space itself becomes hostile. The interstellar medium is thin. On average, maybe 1 hydrogen atom per cubic centimeter. That sounds like nothing. At everyday speeds, it is nothing. At 99% of light speed, those hydrogen atoms slam into your hull with enormous kinetic energy. Each impact becomes a burst of radiation. Dust grains become micro-explosions. The emptiness turns into a storm. You thought empty space was safe. Evidence shows that at relativistic speed, it becomes a radiation hazard. That implies shielding becomes as important as propulsion. You would need thick forward shielding, magnetic fields to deflect charged particles, layers to absorb impacts. All of that adds mass, and mass increases the energy needed for acceleration. The cycle tightens. Now, consider perception. At extreme speeds, the universe does not look the way it does from Earth. Light from ahead becomes blue-shifted. Visible stars shift toward ultraviolet, even X-rays. Light from behind becomes red-shifted, sliding toward infrared and radio. Relativistic aberration squeezes the sky into a bright cone in front of you. At 99% of light speed, most of the visible universe collapses into a narrow circle ahead. Behind you, darkness. The cosmos becomes a headlight. This is not just travel, it is transformation. Now we reach a turning point. You could, in theory, accelerate at 1 Earth gravity continuously, 1g. The same force you feel standing on the ground, comfortable, sustainable. At 1g, after about a year of ship time, you would approach high relativistic speeds. After 2 years, you would be extremely close to light speed. Flip the ship halfway, decelerate at 1g, and you arrive with 0 relative velocity. This constant acceleration profile creates astonishing possibilities. From the traveler's perspective, the journey to the center of the Milky Way, about 26,000 light-years away, could take decades of ship time if you push close enough to light speed. Earth, meanwhile, would age tens of thousands of years. You thought travel was about crossing distance. Evidence shows it is also about crossing time. That implies every long journey is a one-way leap into the future. And now the emotional weight lands. Imagine departing at age 30. You accelerate for years. The stars shift. The sky compresses. Messages from Earth arrive faster and faster as you chase them. But replies take longer and longer to return. If you are heading to a star 100 light-years away at 99% of light speed, Earth sees you arrive roughly 100 years later. You experience far less time, maybe 15 years, but if you send a message home near arrival, that message takes 100 years to reach Earth, and Earth's reply takes another 100 to reach where you are. Conversation dies. You become temporally isolated. You are not just far away, you are out of sync. This is the loneliest trip ever taken. You can outrun your friends, your family, your language, your culture. By the time you return, if you return, Earth has changed beyond recognition. Languages evolve, borders dissolve, species rise and fall, civilizations emerge and vanish. You return as an artifact. The twin paradox is no longer a classroom thought experiment. It is your biography. Fuel doesn't just scale poorly. It detonates your connection to home. The universe doesn't block you. It invoices you. And part of the payment is time itself. But even if you accept that cost, even if you are willing to sacrifice your era, even if you command energy equal to stars, there is still another war waiting. Because the map you are chasing is not static, and the farther you go, the more the map moves. The speed limit doesn't just cap your velocity, it reshapes reality around you. At first, it feels abstract, a number, a constant, the speed of light. C, 186,000 miles per second, clean, precise. But that number is not just about motion, it is about causality. Nothing with mass can reach it. The closer you get, the more the universe resists. Your energy climbs, your gamma factor rises, your clock slows, your length contracts, and something else happens. Your mass behaves differently. Relativistic mass isn't extra matter appearing out of nowhere. It's the way energy contributes to inertia. As you accelerate, your resistance to further acceleration increases. The same thrust produces less and less change in velocity. You push harder, you get less return. You thought acceleration was just about adding energy. Evidence shows acceleration becomes harder the closer you approach light speed. That implies the final stretch towards C is asymptotic. You can approach, you cannot arrive. You can add 9 after 9 after 9 to your velocity percentage. 99%, 99.9, 99.99. Each extra 9 costs exponentially more energy. This is the real face of the antagonist. Not dramatic, not explosive, just unyielding. And while your engine struggles, the sky begins to distort. Imagine you are traveling at 90% of light speed. Look forward. Stars ahead are blue shifted, their light compressed into shorter wavelengths. A yellow star might appear white. A white star might appear blue. Push faster, and visible light shifts into ultraviolet, then into X-rays. Your window must filter radiation that would normally be invisible and lethal. Look behind you. Stars redden, they dim. Eventually they vanish from sight, sliding into infrared and radio frequencies beyond human vision. Now add relativistic aberration. Light that would normally arrive from the sides bends forward in your frame of reference. The entire starfield funnels into a shrinking cone ahead of you. At 90% of light speed, the visible universe compresses into a bright circle roughly 60 degrees wide in front of your ship. At 99%, it shrinks dramatically. The rest of the sky fades to darkness. The cosmos turns into a spotlight. This is where the map breaks. Because navigation itself changes, the constellations you grew up with deform, familiar shapes twist. Polaris is no longer where you expect. Orion collapses into something unrecognizable. You are not just moving through space, you are altering how space presents itself. Now let's bring back the interstellar medium. On Earth, air resistance slows you down. In space, there is no air. That's why Voyager can coast for decades without engines firing. But at relativistic speed, even a near vacuum becomes dangerous. Each hydrogen atom you encounter strikes your hull with enormous energy. The faster you go, the more intense each impact becomes. Dust grains, microscopic and harmless at low speed, become high-energy projectiles. Cosmic rays already fill space. High-energy particles from supernovae and distant phenomena. At near-light speeds, you slam into them faster. Radiation shielding must grow thicker. Magnetic deflection systems must be stronger. The emptiness becomes a barrage. You thought speed was freedom. Evidence shows speed creates new threats. That implies survival at relativistic velocity is as much about protection as propulsion. And then there is communication. Let's say you are traveling to a star 100 light-years away at 99% of light speed. From Earth's perspective, you arrive in roughly a century. From your perspective, because of time dilation, the journey feels much shorter. But information does not care about your perspective. Messages travel at light speed, no faster. If you send a signal home halfway through your journey, Earth receives it decades later. If they reply, their message takes decades to reach where you were when they responded. By the time their reply arrives, you are somewhere else. Conversation fragments. Eventually, communication becomes meaningless, delayed, outdated, disconnected. You can watch Earth's history unfold in accelerated playback if you're chasing its light. Years of broadcasts arriving compressed into months of ship time. But Earth cannot keep up with you. You outrun the present. This is where isolation peaks. You are alone not because of distance, but because of simultaneity. Events that are now for you are not now for them. Relativity doesn't just bend clocks, it bends the meaning of now. Now step back. You have pushed engines to extreme fractions of light speed. You have built shielding thick enough to survive particle impacts. You have accepted that you will age slower than Earth. You have accepted that you will return, if you return, to a future you do not recognize. You think the problem is solved. It isn't. Because the map itself is not static. The universe is expanding. This is not galaxies flying through empty space like shrapnel from an explosion. Space itself stretches. The metric that measures distance grows with time. This expansion is described by Hubble's law. The farther away a galaxy is, the faster it recedes from us, due to cosmic expansion. On small scales, gravity dominates. The Milky Way and Andromeda are moving toward each other. Our local group is gravitationally bound, but beyond that, expansion wins. Now, introduce dark energy. In 1998, observations of distant Type Ia supernovae revealed that the expansion of the universe is accelerating. Something call it dark energy makes up roughly 2/3 of the universe's total energy content and pushes space to stretch faster over time. Dark energy is not a force you can dodge. It does not push your ship directly. It changes the fabric you move through. Here is the critical distinction. The observable universe is not the same as the reachable universe. The observable universe includes everything whose light has had time to reach us since the Big Bang. That sphere extends about 46 billion light-years in every direction. But not everything observable is reachable. There exists something called the cosmological event horizon. It marks the boundary beyond which events happening now can never influence us, no matter how long we wait. Beyond this horizon, space expands so quickly that even light emitted today will never reach us. You thought that if you could see it, you could reach it with enough speed. Evidence shows there are regions whose recession due to expansion outpaces any signal you could send. That implies some destinations are forever inaccessible, even with perfect propulsion. The event horizon currently lies roughly 16 to 17 billion light-years away. Anything beyond it is already slipping beyond causal contact. Even if you accelerate continuously at 1g, even if your gamma factor climbs into the millions, even if your subjective journey lasts decades while the universe ages billions of years, you cannot cross that boundary. The universe doesn't block you with a wall. It stretches the road faster than you can run. And it gets worse. The event horizon is not fixed in a comforting way. As dark energy continues accelerating expansion, more regions cross beyond reach. Galaxies we can observe today will eventually fade beyond our future light cone. The accessible universe shrinks. There is a countdown embedded in cosmology. You thought time dilation was the ultimate trick. Evidence shows cosmic expansion imposes a deeper limit. That implies even relativistic travel has an edge. Now the escalation becomes cosmic. Local anomaly. Voyager barely leaves home. Regional structure. Fusion and antimatter struggle to reach nearby stars. Supercluster scale. Even at extreme gamma, you face isolation. And now, level 4. The unknown horizon. The universe invites exploration. It allows relativistic loopholes. It bends time for those who move fast enough. But it also defines a maximum future reach. And that reach is smaller than the sphere you can see. We are not just limited by speed. We are limited by geometry. Here's the twist that changes everything. The speed limit looks like a prison wall. It isn't. It's a trade agreement. If you can push close enough to it, the universe gives you something back. Time. This is the loophole. Special relativity doesn't just slow your clock a little. At extreme velocities, it transforms distance itself. Let's build this carefully. When you move at high speed relative to someone else, two things happen. Your clock ticks slower in their frame, and lengths in your direction of motion contract in your frame. Time dilation and length contraction are not optional effects. They are built into the geometry of spacetime. The Lorentz factor, gamma, controls both. At low speed, gamma is nearly 1. Nothing interesting happens. At 50% of light speed, gamma is about 1.15. That's mild. 1 year for you equals about 14 months for someone stationary. At 90%, gamma rises to about 2.3. Now, the difference matters. At 99%, gamma is about 7. At 99.9%, gamma climbs above 20. At 99.99%, it exceeds 70. Every additional 9 pushes the time distortion harder. You thought 4 light years meant 4 years at minimum. Evidence shows that from your perspective, the distance shrinks as your velocity rises. That implies the traveler does not cross the same space-time interval the stationary observer measures. Imagine you accelerate to 99.9% of light speed and aim at Vega, roughly 25 light-years away. From Earth's perspective, the journey takes just over 25 years. From your perspective, because gamma is about 22 at that speed, the trip feels closer to 1 year. 1 year to cross 25 light-years. Not by breaking the speed limit, by warping your relationship to time and distance. This is not science fiction. It falls straight out of Einstein's equations. The closer you approach light speed, the shorter the distance becomes in your frame. At extreme gamma, hundreds of light-years compress into distances that can be crossed in decades of ship time. Push further. The Pleiades star cluster sits roughly 440 light-years away. At 99.99% of light speed, gamma above 70, the subjective time for the traveler drops to only a handful of years per 100 Earth years. You could depart in your 30s and reach that cluster before you are old. Earth would age centuries while you age decades. The Milky Way's center, Sagittarius A star, lies about 26,000 light-years from us. It hosts a supermassive black hole 4 million times the mass of the Sunday. From Earth's frame, that's 26,000 years of light travel. But at extreme gamma, you compress that distance. If gamma rises into the hundreds, the subjective journey can shrink into something measured in decades or a bit more. You thought the galaxy was unreachable in one life. Evidence shows that with extreme velocity, the entire Milky Way becomes traversable within extended human time. That implies the scale of reachable space expands with your willingness to pay in energy and temporal separation. Now push beyond the Milky Way. Andromeda Galaxy, our nearest major galactic neighbor, lies about 2.5 million light-years away. From Earth's perspective, light from Andromeda left before humans evolved. But at gamma values in the tens of thousands, the subjective travel time collapses dramatically. 50 years of ship time at gamma 50,000 spans roughly 2.5 million Earth years. You could cross intergalactic space in what feels like a long career. Earth would not be Earth when you arrive. Civilizations would have risen and vanished. Continents might shift. Species would evolve. You would arrive in Andromeda having aged 50 years. Your home would be deep history. This is where the choice sharpens. Relativity allows you to outrun your era. It does not allow you to bring it with you. You thought travel was about distance. Evidence shows it is about how much future you are willing to enter. That implies exploration at cosmic scale is indistinguishable from one-way time travel. Now escalate further. The local group contains dozens of galaxies bound by gravity. Andromeda, the Triangulum Galaxy, dwarf companions, all within a few million light-years. At sufficiently high gamma, a single lifetime could carry you across this entire group. Beyond that lies the Virgo cluster, over 50 million light-years away, thousands of galaxies bound together. In principle, if gamma climbs high enough, that too falls within a subjective lifetime. You see the pattern. Every time you add a 9 to your velocity percentage, the reachable map stretches outward. Length contraction squeezes enormous cosmic structures into distances that your ship can cross in decades. But here is the hidden clause. Gamma does not just shrink distance, it amplifies the energy required. To push gamma into the tens of thousands requires energy beyond anything our civilization can currently conceive at scale. Each step toward higher gamma multiplies the cost. Space isn't far, it's expensive. And the invoice grows faster than the benefit. There's another complication. Continuous acceleration at 1g feels comfortable, but sustaining that acceleration for years requires immense power and structural integrity. At 1g, after about a year of ship time, you approach relativistic velocity. After 2 years, you are extremely close to light speed. After 3, you are adding more 9s, but at enormous energy cost. Flip at midpoint, decelerate symmetrically. From your perspective, you experience constant gravity, a floor beneath your feet. From Earth's perspective, your journey spans thousands, millions, or billions of years depending on the target. The twin paradox becomes civilization scale. You thought coming back meant returning home. Evidence shows returning means arriving in someone else's future. That implies round trips beyond modest distances sever your original timeline permanently. Now we confront a deeper issue. Even if you reach Andromeda, even if you traverse the local group, you cannot escape cosmic expansion indefinitely. Dark energy accelerates expansion. Over immense timescales, galaxies beyond our local group drift beyond the cosmological event horizon. Light emitted today from some distant galaxies will never reach us. And even if you depart today toward a galaxy near that horizon, expansion during your voyage may carry it beyond reach. The map shrinks while you chase it. You thought infinite time and infinite velocity meant infinite access. Evidence shows geometry and expansion define a finite, reachable region. That implies the maximum distance one lifetime can span is bounded not only by speed, but by the universe's expansion history. Still, within those bounds, the range is staggering. A single human life, measured subjectively, could encompass journeys across the entire Milky Way, across neighboring galaxies, across clusters. The laws of physics do not forbid it. They demand payment, energy, engineering, isolation, sacrifice, and now the emotional axis returns. You are offered the stars, but the ticket is one way through time. You can reach the stars, but you cannot bring anyone with you. This is the part no propulsion diagram shows. At 99.9% of light speed, your gamma factor climbs above 20. Time for you slows dramatically compared to Earth. Distances in front of you contract. The galaxy compresses into something crossable. From inside the ship, it feels like progress. From Earth, it looks like abandonment. Imagine departure day, launch, acceleration at 1g. The steady push feels like standing on Earth. Coffee stays in the cup. Feet stay on the floor. Outside, The sun shrinks, planets collapse into bright dots. The heliosphere becomes a memory. Weeks pass on board, months. On Earth, years tick by. Messages flow at first, video calls with delay, then hours of delay, then days, then months. Soon, every conversation becomes a time capsule. You record a message. It takes years to arrive. Their reply takes years to return. You are already elsewhere when it reaches you. Light time becomes emotional time. You thought distance was the painful part. Evidence shows delay is worse. That implies isolation begins long before you leave the solar system. Push further. At relativistic speed, something strange happens when you look forward. Relativistic aberration funnels starlight into a tight cone. The entire Milky Way bends toward your direction of travel. Behind you, stars fade into darkness, redshifted beyond sight. Your universe narrows. The sky you grew up with disappears. Constellations dissolve. The familiar band of the Milky Way stretches and brightens ahead, blue-shifted, compressed. It's beautiful. It's terrifying, because the view confirms something final. You are not just far from home. Home is no longer in your sky. And then comes radiation. Cosmic rays, high-energy particles from supernovae and distant active galactic nuclei, slam into your shielding. The interstellar medium, sparse hydrogen atoms drifting between stars, strike your hull at near light velocity. Each impact carries enormous kinetic energy. Even microscopic dust grains become explosive at these speeds. Your ship must carry heavy shielding, magnetic fields to deflect charged particles, layers of material to absorb secondary radiation. Mass grows. Energy requirements grow. The invoice rises again. The universe doesn't block you, it invoices you. Now imagine the halfway flip. After years of acceleration, you rotate the ship. Engines fire in reverse. Deceleration begins. Gravity still presses you to the floor, but now, light from your destination redshifts. The blue-shifted glare softens. The star ahead swells in size. If your target is Proxima Centauri, the nearest star, you see it resolve into a bright red disk, a dim red dwarf. If your target is Vega, a brilliant white star 25 light-years away, it becomes a blazing presence. If your target is Sagittarius A star at the center of the Milky Way, the star density ahead increases. The sky fills with clustered light. But here's what Earth sees. They see your ship depart. They track your radio signal as it stretches and fades. They wait for confirmation of arrival. If your destination is 25 light-years away, they wait over 25 years. If it's 100 light-years away, they wait a century. If it's Andromeda, they will never hear from you in their lifetime, nor their children's, nor their descendants, for thousands of generations. You thought the loneliness was about physical distance. Evidence shows it's about temporal divergence. That implies the deeper you go, the more you sever. Now consider return. You reach Vega in 1 year of ship time, thanks to extreme gamma. You study, you orbit, you record data. You turn around and accelerate home. From your perspective, perhaps 2 or 3 decades have passed. From Earth's perspective, 50 years, maybe more. Your friends are gone. Your parents are gone. The language has shifted. Technology has evolved beyond what you left. You are a visitor from the past. Push the scale further. Travel to Andromeda at extreme gamma. 50 years for you, 2.5 million years for Earth. Humanity as you knew it is gone. Maybe humanity itself is gone. You arrive back to a planet transformed by evolution and geology. Continents drift inches per year. Over millions of years, coastlines reshape. Ice ages come and go. Species branch and vanish. You are no longer returning home. You are arriving in deep time. This is peak 2. Not the shock of scale, the silence. Because even if your mission is scientific, even if your crew is trained for isolation, even if you bring archives and art and recordings, there is no real-time conversation, no shared present. Relativity does not allow a universal now. Simultaneity is relative. What is happening now on Earth depends on your velocity and position. You and Earth inhabit different slices of space-time. You can never truly share the same moment again once you commit to extreme relativistic travel. You thought time dilation was a gift. Evidence shows it is also a wedge. That implies every relativistic explorer becomes temporally displaced. Now zoom out again. The Milky Way is about 100,000 light-years across. At sufficient gamma, you could cross it in a human lifetime of ship time. But crossing it means Earth ages 100,000 years. By the time you reach the far side and return, Earth has changed beyond recognition. Languages have turned over thousands of times. Civilizations have risen and collapsed repeatedly. Perhaps your species has evolved into something else. Your journey becomes a bridge across geological epochs. And still, even that is not the final wall. Because beyond the Milky Way lies the local group. Beyond that, the Virgo cluster. Beyond that, the cosmic web stretching across hundreds of millions of light years. With extreme gamma, clusters fall within subjective reach. But cosmic expansion continues. Dark energy accelerates the stretching of space. Over billions of years, galaxies beyond the local group drift beyond our cosmological event horizon. If you leave too late, some destinations will already be unreachable. The reachable universe is not static. It changes with cosmic time. You thought speed was the only variable. Evidence shows timing matters too. That implies there is a window for cosmic exploration, and it does not last forever. This is the loneliest realization. You can chase the stars. You can bend time. You can cross distances that feel impossible. But you cannot hold onto the era you left. And you cannot reach everything you can see. The map is finite. The present is fragile. And the deeper you travel, the more you become a relic of your own origin. Now imagine you have the engine. Not chemical, not ion, not fusion barely scraping 10% of light speed. Something far beyond. Antimatter. Perfect shielding. A civilization that can feed you energy like a star feeds its planets. You are ready to choose a target. Open the map. First layer, the Milky Way. 100,000 light years across. A barred spiral galaxy with hundreds of billions of stars. Our Sun sits in a minor arm called the Orion Arm, orbiting the galactic center once every 200 million years. At extreme gamma, you can cross it in decades of ship time. Sagittarius. A star waits at the center. A supermassive black hole 4 million times the mass of the Sunday. Around it, stars whip at incredible speeds, tracing tight orbits in a gravitational ballet. You could watch that dance up close. But Earth would age tens of thousands of years. Civilization would become archaeology. Second layer, the local group. Andromeda Galaxy, also known as M31, looms 2.5 million light-years away. A spiral galaxy larger than the Milky Way, on a collision course with us in about 4 billion years. At gamma high enough, you could reach Andromeda in a lifetime of ship time. From Earth's perspective, millions of years pass. You arrive in a galaxy where no human signal has ever been heard. You return to a planet where no one remembers your launch. Third layer, the Virgo cluster, over 50 million light-years away. Thousands of galaxies bound together in a massive gravitational structure. The cluster sits within the larger Laniakea supercluster, a flow of galaxies drifting toward a region known as the Great Attractor. These are not poetic names. They are measurements of structure. The cosmic web stretches across space like a three-dimensional spiderweb. Galaxies gather along filaments. Vast voids yawn between them. At extreme relativistic speeds, even these scales compress in your frame. You thought clusters were abstract. Evidence shows they are destinations if you are willing to enter deep time. That implies the observable universe becomes a navigable chart subjectively. But now we reach the fracture. Because not everything observable is reachable. The universe has been expanding since the Big Bang. That expansion is described by the scale factor in cosmology, governed by the Friedmann equations. On large scales, galaxies are not moving through space like bullets. Space itself stretches between them. Hubble expansion tells us that the farther away a galaxy is, the faster it recedes. For nearby galaxies, gravity overcomes expansion. The Milky Way and Andromeda are moving toward each other. The local group is gravitationally bound. But beyond that, expansion dominates, and dark energy accelerates it. Dark energy behaves like a constant energy density built into space. As space expands, more space appears, and with it, more dark energy. The expansion does not slow down, it speeds up. Now picture this. There exists a boundary called the cosmological event horizon. It is not a physical wall, it is not visible, it is a limit in space-time. It marks the maximum distance from which light emitted now can ever reach us in the infinite future. Anything beyond that boundary is causally disconnected from our destiny. You thought that if you could see a galaxy, you could eventually reach it. Evidence shows that some galaxies we see today are already beyond the horizon for any signal we send now. That implies visibility does not equal accessibility. Right now, the observable universe extends about 46 billion light-years in radius. But the cosmological event horizon is much closer, roughly 16 to 17 billion light-years away. That is the edge of the reachable future. Even if you accelerate at 1g forever, even if your gamma factor climbs into absurd values, even if your subjective journey spans decades while the universe ages trillions of years, you cannot reach beyond that horizon, because space between you and those regions expands too quickly. Faster than light can close the gap. This is not a violation of relativity. Nothing locally exceeds light speed. It is the metric of space itself that grows. You can run as hard as physics allows. The road lengthens beneath you. You thought speed was the ultimate key. Evidence shows geometry defines the ultimate cage. That implies the universe is larger than any possible expedition, and the cage is subtle. Galaxies near the horizon are not static. Over billions of years, more galaxies cross beyond reach. They fade, their light redshifts. Eventually, distant clusters disappear from the sky entirely. In the far future, observers in our local group will see only merged remnants of the Milky Way and Andromeda. The rest of the cosmic web will slip beyond the horizon, invisible and unreachable. The accessible universe shrinks with time. There is a countdown embedded in cosmology. You thought exploration was open-ended. Evidence shows there is a window. That implies the best time to explore the universe is now, before more of it drifts away. Now bring this back to the human scale. One lifetime, 80 years, perhaps. At Voyager speeds, you never leave the sun's outer cloud. At fusion speeds, you reach nearby stars in centuries. At extreme relativistic speeds, you can cross galaxies subjectively in decades. But no matter how high your gamma climbs, you cannot outrun dark energy's ultimate boundary. You cannot reach everything, and here is the final escalation. Even within the reachable region, time dilation guarantees that every far journey becomes a leap into the future. You cannot explore and remain synchronized. You cannot push to the cosmic horizon and still belong to the moment you left. The speed limit is not just a number, it is the rule that binds space, time, energy, and destiny together. Space isn't far, it's expensive, and the price is paid in fuel, in radiation shielding, in engineering beyond stars. But the deeper cost is temporal. Every light year you cross at relativistic speed moves you further from your original present. Every additional 9 in your velocity percentage pushes you further into Earth's future. The reachable universe is vast, but it is not infinite, and your lifetime, stretched by relativity, is powerful. But it is not absolute. The map is big. The window is finite. We've pushed engines to their limits. We've bent time. We've crossed galaxies in theory. We've watched the cosmic web stretch beyond reach. Now we hit the final wall. Not a wall of speed, a wall of timing. The universe is about 13.8 billion years old. Since the Big Bang, space has expanded and cooled. Matter condensed into galaxies. Stars ignited. Planets formed. Life emerged here, on one small world orbiting an ordinary star in the Milky Way. For most of cosmic history, expansion was slowing down. Gravity pulled matter together, resisting the outward push. Then dark energy took over. About 5 billion years ago, expansion began accelerating. Not dramatically at first, but steadily, relentlessly. Dark energy doesn't dilute as space expands. It stays constant per unit volume. That means as space grows, total dark energy increases. The push strengthens. The scale factor of the universe grows faster and faster. Now, picture a distant galaxy right at the edge of our cosmological event horizon. Its light reaches us today. We see it as it was billions of years ago. If we launch toward it now, accelerating at 1G for years, pushing gamma higher and higher, compressing distance in our frame, chasing its ancient light, we still might never reach it. Because while we travel, space between us and that galaxy expands. If the rate of expansion outpaces our ability to close the gap, the destination recedes faster than we can gain ground. You thought infinite patience plus near light speed meant inevitable arrival. Evidence shows some roads lengthen faster than you can run. That implies the reachable universe is a subset of the visible one. Now, let's clarify something subtle. The observable universe is defined by light that has had time to reach us since the cosmic microwave background was released, about 380,000 years after the Big Bang. The CMB is the oldest light we can see, a faint microwave glow filling the sky, a snapshot of the early universe. Beyond that, the universe exists, but we cannot see it because light has not had time to reach us. The cosmological event horizon is different. It marks the boundary beyond which events happening now will never affect us in the future. These two horizons are not the same. The observable universe is larger than the reachable future universe. You can see farther than you can ever go. That flips the entire map. You thought visibility defined possibility. Evidence shows causality defines possibility. That implies our cosmic future is bounded in a way our eyes alone cannot reveal. Now compress this to a single human life. You board a relativistic spacecraft. You accelerate for years. Gamma rises into the thousands. Distance contracts in your frame. You cross millions of light years subjectively in decades. From your perspective, clusters and superclusters drift past in reasonable time. From Earth's perspective, billions of years pass. By the time you approach the edge of the reachable universe, Earth is ancient history. The Sun may have expanded into a red giant. The Milky Way and Andromeda may have merged into a single elliptical galaxy. Your origin star could be gone. And yet, even with all that temporal sacrifice, there is a line you cannot cross. Beyond it, galaxies recede forever. This is the final invoice. The universe doesn't block you, it invoices you. It charges energy to approach light speed. It charges isolation to use time dilation. It charges history to travel far. And it charges geometry to define your ultimate reach. Space isn't far, it's expensive. Now look at the numbers in human terms. If you left Earth today and accelerated at 1G halfway to the center of the Milky Way, then decelerated at 1G, your subjective journey might take a few decades. Earth would age tens of thousands of years. If you aimed for Andromeda at extreme gamma, your subjective time might be 50 years. Earth would age millions. If you aimed near the cosmological event horizon, pushing physics to its edge, you might experience a century. Earth would age billions. Your journey would span the rise and fall of stars. But even then, there would be galaxies forever beyond. The last reveal is the one you can't engineer around. The universe is not infinite in what it allows you to touch. It is only infinite in what you can observe. An observation without contact is a different kind of distance. Now step back to level 1, Voyager drifting outward, barely a light day away after decades. Level 2, fusion dreams, antimatter fantasies, relativistic shielding. Level 3, galaxies, clusters, the cosmic web. Level 4, the horizon. This flips the whole map, because the question was never just How far can you go in one lifetime? The deeper question is, how much future are you willing to enter? Relativity gives you the power to compress distance. Dark energy defines the edges of your playground. Between them lies your reachable universe, and it is vast beyond imagination, yet not infinite. Now we are ready to answer the question fully. What is the maximum distance a human can travel in one lifetime? Not at Voyager speed, not at fusion speed, at the limit allowed by physics. The answer depends on how much energy your civilization can command, how much isolation you can endure, and how much of Earth's future you are willing to miss. With extreme relativistic travel, you could cross the Milky Way. You could reach Andromeda. You could traverse much of the local group. Push further, and you could approach clusters tens of millions of light years away. But you cannot exceed the cosmological event horizon. That boundary defines the maximum sphere of influence of your entire future. Your lifetime, stretched by relativity, can carve a path across an enormous portion of that sphere, but not beyond it. The reachable universe is finite, and your life, even when bent by physics, is a thread within it. Now we turn to the only part that actually matters. What this means. What this actually means. Not in equations, not in propulsion charts, not in gamma factors and horizons. What does it actually mean for you here, now? First, your life is already relativistic. You are standing on a planet orbiting a star that moves around the Milky Way at over 500,000 miles per hour. The Milky Way itself drifts within the local group. The local group flows toward the Virgo cluster. Everything sits inside an expanding universe driven by dark energy. You are not static. You are riding space-time. We tend to think of travel as leaving, as escape, as motion away from where we are. But you are already moving through the cosmos at astonishing speed. Every second, you travel hundreds of miles just because Earth rotates. Every year, you travel hundreds of millions of miles around the Sunday. Over your lifetime, you trace a spiral path through the galaxy, thousands of light years long. You thought you were stuck. Evidence shows you are already embedded in a vast cosmic journey. That implies perspective matters more than propulsion. Second, distance is not the real barrier. Time is. The speed of light doesn't just limit how fast you can go. It defines how cause and effect work. It defines what can influence what. It defines which events can ever touch your life. The cosmological event horizon is not just a boundary for spacecraft, it is a boundary for meaning. There are regions of the universe that will never, ever affect us. Not because we are weak, not because we are primitive, but because space-time itself says no. You thought the universe was fully open if we just tried hard enough. Evidence shows reality is structured with limits. That implies meaning is local. Not small, local, our galaxy, our local group, the stars we can actually reach within deep time. That is our causal neighborhood, and within that neighborhood, the scale is still overwhelming. Hundreds of billions of stars in the Milky Way alone, trillions of planets across the observable universe, structures stretching across hundreds of millions of light years. But the part we can ever touch is finite. That makes it more precious. Third, every extreme journey is a trade. Relativity allows you to compress distance by sacrificing synchronization. You can cross galaxies in decades of your own time, but you must give up your era, your present, your shared now. The universe doesn't block you, it invoices you. You can pay in energy. You can pay in isolation. You can pay in centuries of separation, but you cannot avoid payment, and that reframes the question. The real question was never just, how far can you travel in one lifetime? It was, what are you willing to leave behind? If you accelerate toward Andromeda at near light speed, you will get there in a lifetime of ship time, but you will arrive millions of years after you left. Everyone you knew will be gone. Every institution, every culture, perhaps even your species as you understood it. You will not just explore space. You will time travel into a future that has no memory of your departure. That's not just physics. That's existential. So what does this mean for us, right now? It means the most extraordinary journeys we can take in our lifetime are not measured only in miles or light years. They are measured in connection, in shared present moments, in the fragile, temporary overlap of consciousness that relativity allows before paths diverge. You don't need antimatter propulsion to experience the vastness of the cosmos. You already live inside it. When you look up at Andromeda, you are seeing light that left before humans built cities. When you look at the Milky Way, you are seeing photons that began their journey before you were born. Observation is a kind of travel. Light bridges distance without aging you. And that may be the most profound gift physics gives us. Because while the reachable universe is finite, the observable universe is immense. You can see farther than you will ever go. You can witness events that happened billions of years ago. You can hold the deep past in your eyes. You thought exploration required leaving Earth. Evidence shows the cosmos arrives here every night as light. That implies curiosity does not need propulsion to be satisfied. Now, zoom out one final time. Voyager drifts outward. It will pass near stars in tens of thousands of years. It carries a golden record, sounds of Earth, greetings in dozens of languages, music, the whisper of our existence. It will never reach another civilization in our lifetime, but it is a statement. We are a species that looks at the horizon and asks what lies beyond, even knowing the limits, even knowing the invoice, even knowing there are regions forever unreachable. We ask anyway, and maybe that is the point. The speed limit is not a punishment. It is structure. Dark energy is not cruelty. It is geometry. The cosmological event horizon is not a wall. It is a definition of our arena. Within that arena, the scale is staggering. You could, in principle, cross the Milky Way in a lifetime. You could reach Andromeda if you accept the loss of your present. You could traverse much of the local group before expansion seals parts of it away. That is not small. That is not limiting. That is extraordinary. But here is the final shift. Your lifetime is not defined only by how far you can travel through space. It is defined by how you use the slice of space-time you are given. You are a brief fluctuation of ordered matter in a universe 13.8 billion years old. You are riding a planet orbiting an average star in a galaxy among trillions, and yet you can understand cosmic expansion. You can calculate the Lorentz factor. You can predict the existence of an event horizon billions of light years away. You can hold the structure of space-time in your mind. That is the real miracle. Not that we can cross galaxies, but that we can comprehend them. Space isn't far, it's expensive, but understanding is cheap. All it costs is attention, and that might be the one thing that lets us travel farther than any engine ever will.